Hi, in this video, I'll continue our journey into basic topology, where today we'll talk more about the different type of topologies that are common. So we have already seen some common topologies that are quite basic, such as the discrete one, or the trivial one, or even the metric space topology, but that's not so trivial. And now we want to talk about this thing known as the subspace topology. And so what is the subspace topology? Well, when we are given X and a topological space T, if Y is a subset of X, then it's natural to question what is the topology defined on Y. And so the subspace topology is defined to be the collection of Y intersect U where U is open in X. So U is open in X and Y intersect U will be open in Y. With this topology, Y is called a subspace of X and the open sets consist of intersections of open sets of X with Y. We can then easily check that this will form a topology, and I'll leave it to you to see. And if you have a basis, then the basis of the subspace topology on Y will be just the basis intersecting with Y. And again, you can check that because given open in U, there exists and a Y in U intersect Y, then you can choose a basis element in collection of B such that Y is an element of B, which is a subset of U by the property of basis. And because of that, when you intersect it now, Y will still be inside this, and this will still be a subset of U intersect Y. And hence, by the lemma in the previous video, we can say that this will form a basis for the topology. But when dealing with such notions, it's good to understand that or take note of when we want to talk about openness in which space. So when we say a set is open in Y, we really mean that it belongs to the topology on Y. And that being said, it depends on the topology on Y what sets are open. And when we say that U is open in X, it belongs to the topology of X. So it really depends on the topology defined. So a set may be open in Y, but it is not an open set in X. And a simple example is if we take a interval from A to B, then this open interval is of course open when we regard it to a subset in R1, but it's not an open set when we regard it as a subset in R2. And you can check why is that so. Hence, when we define openness, it really depends on what the topology is. So while you intersect with an open set Y, this may not be an open set again in X. And so when will it be? Well, if Y is a subspace of X, means it is given a subspace topology, then if this set is open and Y is open in X, then we can confirm that U will be open in X. And the proof is simple because Y is open in X and U equals to Y intersect V, and this is open in X. Y is open in X, and so U being an finite intersection of open sets will also be open, and we are done with that. And with this subspace topology now, we can define the inclusion map, where A is a subspace of X. We can say that this inclusion map will be continuous, and that's because for any U open in X, when you pre-image it, it'll be just U intersecting A. And so this is open by definition of the subspace topology. And we have some proposition that if you just take a subspace, then for any map from any topological space to A, F0 will be continuous if and only if the inclusion map composed with F0, that means T to X, is continuous. And so if F0 is continuous, then since the inclusion map is continuous, of course the composite will be continuous. And we can again use that if the composite is continuous, that means that for all open in A, there exists, then we want to prove that for any given, we want to prove that F0 is now continuous. And that means for all open in A, you can find the pre-image will also be open. And so you just take an open set in A, which equals to A intersecting an open set in U in X, which is U, and this is really the pre-image of the inclusion map. And so this will be F inverse image of F with the inverse image of J of U. And that's really saying that's the inverse image of J circle F0. And as a result, this will be open by continuity of J circle F0. And hence F0 is continuous. And so we can really say that F0 is continuous if and only if the inclusion map composed with F0 is also continuous. And that only works for subspace topologies. So it's a very useful property for subspace topologies to have. The next style of topology that we want to talk about, that is also very common, is known as the product topology. And basically, the product topology is defined between two topological spaces, and you just take the Cartesian products of the two spaces. So you can think of it as a real line, and then now you have the y-axis. So it's the whole plane space now. And the product topology is the topology of the collection of, the basis will be a collection of all the sets such that U cross V of the form U cross V, and then U is open in X and V is open in Y. And again, I'll leave it to you to read that you can easily verify that this is a basis. And so when B is a basis of X and when script C is a basis for Y, then the collection D will equals to B cross C, where B is in an element of the basis of X and C is an element of the basis of Y. And this D will now form a topology on a basis for the topology on X cross Y. Again, the idea is similar to what we have already done where we always deal with basis, is that the reason why we do this is because you want to know how to describe the set. The open sets. And so those proofs, I'll leave it to you to read in the textbook. And so now we want to define the projection map, which is basically from X cross Y, we want to go into X. And so we define the projection map from, so we are given a coordinate, we just want to take the X coordinate basically. And basically, the maps pi1 and pi2 are called the projections of x cross y onto the respective coordinate. And you can easily show that these maps are continuous, which I'll again leave it to you to read in the textbook, because this is not the main focus of what we want. Instead, what we want now is that we want to prove that if we pre-image these projection maps and take the union, then it forms a sub-basis for the product topology. So now I'll go through the proof. If we let T be the product topology on x cross y, and T prime be the topology generated by this sub-basis, because every element of S belongs to T, so does the arbitrary union and finite intersection. And so obviously, T prime is a subset of T. On the other hand, every basis element is a finite intersection of elements of the sub-basis. And since U cross V equals to the pre-images intersecting each other, therefore U cross V belongs to the topology T prime. And so the topology T must be a subset of T prime. And we are done. I hope this is clear, and the reason why we want to talk about this collection is now that it will actually help us, because this notion over here can help us generalize now to more than two products. And it can actually, this is the notion that you use to generalize to infinite products, but we shall not go into that because we rarely deal with the infinite products in this level. And if you want, you can read up more about it, or stay tuned when we do a whole course about topology. So for this tutorial, we'll just continue and introduce more ideas about topologies that are important. And one of them is a map into now the product space. So previously we talked about product space mapping into the X or Y, and those are the projections. Now we want to take a function that brings an element from A to X cross Y. And so this is the function defined, where F1 and F2 are also functions. And we say that this F is continuous if and only if in each coordinate F1 and F2 are continuous. And let's see the proof. So we let pi1 and pi2 be projections onto the first and second vectors. Then these maps are continuous. So we know that if F is continuous, then F1 and F2 being composite of continuous maps, because F1 is now pi1 of Fa, it will therefore be continuous. And so that proves one direction. Conversely, suppose that F1 and F2 are continuous, then we shall show that the basis element of U cross V for the topology of X cross Y, its inverse image is also open. So a point A is in F cross the inverse image of U cross V if and only if Fa is an element of U cross V. And because Fa is an element of U cross V, it means that F1A is an element of U and F2A is an element of V. And so it results back into this scenario over here, where the pre-image of U cross V is the pre-image of U intersecting the pre-image of V for F1 and F2 respectively. And since F1 and F2 are both continuous, this will be open and this will be open, which means that this whole thing will be open, and so will be the intersection. So take a look at this picture to understand. When you inverse image or open set in one of the coordinates, it expands it now into, because this side is not taken into account, so it just captures everything here, so it turns it into one big rectangle now. And similarly for this side, you go into one horizontal rectangle. And so when you intersect them, you still become a rectangle, which is considered open in the product topology. So for product topologies, you can really think of them as rectangles. So while we have a good criteria for continuity into products, there's actually no good criteria for continuity from products into a random space. You might think that it's continuous if and only if it's continuous in A and B respectively, but it is not true, and it's an exercise in Macrin's topology to prove that this function is continuous in each variable, but the overall function is no longer continuous. And I'll leave it to you. That's all for this video. Feel free to like, share and subscribe, and I'll catch you in the next video. Bye!